Welcome to our channel, Square Ekpatshala, your home for physics mastery. Today, we are walking step by step through the three most important 5-mark derivations in electrostatics, securing the math you need for your upcoming board exams. We begin with an electric dipole. This is simply a system of 2-point charges, equal in magnitude but opposite in sign, separated by a very short distance. We measure the strength of this setup using the electric dipole moment. To find it, you simply multiply the magnitude of one charge by the total distance between them. The dipole moment is a vector quantity, and its direction is always measured from the negative charge toward the positive charge. Let's find the electric field at an axial point, P, located a distance r from the dipole's center. Looking at the geometry, the distance from the positive charge is r minus L. From the negative charge, it is r plus L. The positive charge pushes its field away from the dipole, while the negative charge pulls its field back. Because the positive charge is closer, its outward push is stronger. We subtract the weaker inward field from the stronger outward one to calculate our net axial field. Now we move point P above the center, onto the perpendicular bisector, the equatorial position. Using the Pythagorean theorem, the diagonal distance from both charges to this point is identical, the square root of r squared plus L squared. With identical distances producing identical field magnitudes, we break the vectors into components to find the net effect. The vertical sine components face opposite directions and cancel out to 0. The horizontal cosine components point in the exact same direction and add together. In cases where the distance r is much larger than the dipole itself, both field strengths decrease following an inverse cube relationship with distance. When we compare these results, the magnitude of the axial field is exactly twice as strong as the equatorial field. Moving past isolated point charges requires an understanding of continuous flow. Electric flux is the total count of electric field lines passing perpendicularly through a given surface area. To calculate this mathematically, physics treats physical area as a vector. The area vector always points perfectly perpendicular, straight outward from the surface, regardless of how the surface is angled in space. The flux depends strictly on the angle between the electric field lines and this area vector. At 0 degrees, they align for maximum flow. At 90 degrees, the field lines slide flat across the surface, resulting in 0 flux. At 180 degrees, the lines enter backward, creating a negative inward flux. This geometric reality forms the basis of Gauss's law. It states that the total outward electric flux through any closed boundary equals the enclosed charge divided by the permittivity of free space. The actual shape of the physical boundary does not change the math. Let's test that logic. If you enclose a complete electric dipole inside a box, where the positive and negative charges sum to a net charge of 0, what is the total outward flux? It is exactly 0. Now we apply Gauss's law to an infinitely long, uniformly charged wire. We measure the charge here using linear charge density, lambda, which tells us the amount of charge per unit of length. To derive the field at a given distance, we imagine a cylindrical Gaussian surface enclosing a segment of the wire. We separate this cylinder into 3 mathematical zones: the top flat circle, the bottom flat circle, and the curved outer body. The positively charged wire pushes its electric field outward horizontally. The area vectors for the top and bottom faces point vertically, sitting at a strict 90-degree angle to the field. As we established, a 90-degree angle means absolutely 0 flux escapes through these flat ends. We calculate the flux as the field E multiplied by the curved surface area, 2 pi RL. By Gauss's law, this must equal the enclosed charge, which is the density lambda times the length L divided by epsilon naught. When the length L cancels out from both sides, we arrive at the final field equation, lambda divided by 2 pi epsilon naught r. This chart shows the resulting relationship. Because distance, r, sits in the denominator, the electric field is inversely proportional to how far you are from the wire. The field strength drops steadily as you move away. To solve numerical problems for the infinite wire quickly, multiply both the numerator and the denominator by 2. This yields a 4 chi epsilon naught on the bottom, letting you drop in Coulomb's constant, K, and bypass messy fraction math. This chart summarizes the core relationships. Remember the dipole direction? the 2-to-1 axial ratio, the negative sign on inward flux, Gauss's base equation, and the inverse relationship for charged wires. Take a screenshot of this list right now to use in your studies, and join us on Square Egg Pathshala for more clear, step-by-step physics mastery.